Hi, Year 12. Hope you're well. The submission questions yesterday were quite lengthy solutions, weren't they? So I'm not going to go through them now. Obviously, those of you who have attempted them, I've already marked them, but I urge you to have a go at those because those two techniques, gradient of tangent, gradient of normal, absolutely crucial. But I said we would look at a different application of differentiation today, and that's what we're going to do. Now, do you remember when we were sketching cubics? So I know that this cubic function, if I multiplied it out, is going to be a positive cubic, so it's going to be a happy cubic. Those are the ones that start low and finish high. And I know it's got roots at -2, +1, and +3. So I can have a stab at sketching it. I also know if I multiplied this out, the constant term would be 2 times -1, which is -2, times -3, which is 6. So I know it's going to cross the y-axis up here. So I know it's that shape and it crosses there. So it's going to look something like that, isn't it? And do you remember when we did this, I said, yeah, so we know where that is, and we know where that is, and we know where that is, and we know where that is. But what we don't know are these places here, the location of the turning points. I know, because what I know about cubics, I know this is a maximum here, and I know this is a minimum here. And I know when I have a quadratic, I can locate the turning point by completing the square. But until now, we haven't had a way of finding the turning points on other functions, cubics or more complicated functions, except we now do. Can you see how we can use differentiation? The key thing is that at a turning point, at a maximum or a minimum, the gradient of the curve is temporarily 0. The curve will be horizontal, just for an instant, because of course the gradient of the curve is always changing. But for an instant, it will have a gradient of 0. And here, similarly, it will have a gradient of 0. So, if we can find dy by dx, we just need to ask, when will dy by dx equal 0? We can locate the turning points by asking, when is dy by dx 0? So that's my objective for today. Finding turning points by asking, when does dy by dx equal 0? Now, of course, that doesn't give me a way of distinguishing maximums from minimums because the gradient is 0 at both. So I do need a little bit more thought involved, but in this case, I know what the graph looks like. I know about cubics, so hopefully I'm going to be able to finish my sketch using differentiation. Okay, so can I get you to multiply that out for me to get the function as a y equals function with x cubes, x squared, x is in a constant term? We can't differentiate this because it involves terms being multiplied. We can only differentiate things where we've got terms being added. So first job, multiply that out for me to give me a y equals function, and I'll come back when you've done that. Okay, so I multiplied the first two brackets and then multiplied by x plus 3, so that gives me x cubed. Always stripy, isn't it? So I've got -3 plus 1, so that's -2 x squared minus 5x plus 6, so that's my turning point. So I can now differentiate this. So dy by dx, 3x squared multiplied by the power, reduce the power by 1, minus 4x minus 5, 6 disappears. So to find the turning points, I just have to ask, when does that equal 0? When does the gradient equal 0? Remember, this is a formula for the gradient. What we were doing yesterday was substituting values of x into that to work out the gradient when x is this and when x is that. We're now doing the reverse. We're saying find the values of x when this is equal to 0, when the gradient's equal to 0. Okay, go on then, solve that. You're probably not going to get particularly nice numbers. And then don't forget to work out the coordinates. We need the y values, so we have to take our x values, substitute them into our original function. Okay, so I've got my two x values, not particularly nice values. I'm not going to use the rounded values to work out the y values. I'm going to use the exact values. So remember, to work out the y values, I need to go back to the original function, not dy by dx, the original function. So I'm going to use my calculator for that. So I've made x equal to 2 plus root 19 over 3, and I've just typed that in. So that's the value I get here. So that's minus 4.06. That's my y value when I get that. And then if I go back up here and just change that to 2 minus, it re-evaluates it all for me. Boom, boom, there we go, 8.21. And if I zoom out and look at that in the context of the original sketch, can't quite zoom out far enough, sadly. Let's try that. Focus. Then, okay, so this point here must be that one. So this is my maximum point here, and this point here must be that one. That's my minimum point there. So what I have done is I've completed the picture. I knew the roots, I knew the y-axis intercept, and now I've done the bit that we hadn't previously been able to do by using differentiation to locate the turning points. Now that's a full question with not very nice round values. So for the rest of today's lesson, I'm just going to look at some more straightforward examples of finding turning points, just to practice this technique. Really, really easy. What we haven't yet covered is how do we work out when they're maximum or minimum if it's not a function that we know about, but that will come later. Let's move on to some more practice then. The first point to make is that there are three sorts of turning points. We know about maximum and minimum points, but you also get a point like this. There's one in the graph of y equals x cubed, which are called inflections. And you can get downhill inflections as well that sort of look like this. So they are places where the gradient is instantaneously 0, horizontal, but they're not a maximum or they're not a minimum. So there are three sorts, and not today, but in a subsequent lesson we'll look at how we can tell between them. There's another term we ought to introduce. This is a maximum point, but it's not the highest point on the whole function because the function gets higher over here. So this is sometimes referred to as a local maximum. Not all maximums are local. Some of them are genuinely the highest point that the graph reaches. And similarly, this is a local minimum because although it's a minimum point, the graph is lower elsewhere. Okay, so let's practice finding turning points. So let's start with quadratics. Now, of course, we've got a way of finding the turning point of quadratics already, completing the square. Notoriously fiddly, so nice and easy now. Let's differentiate it. So that would be 4x minus 5. I want to find the turning point. I know it's a happy one, so I know it's a minimum point. So I just ask, when does that equal 0? And if I want to know the coordinate, then I substitute that into my original function, and that gives me the value that I'm after. And magically that appears. So go on, have a go at finding the turning point of this one. I knew that's a minimum. So go through the same process with that one. Pause and have a go. Okay, so I differentiated, so that 7 disappears, minus 6x becomes minus 6, and 2 times minus 3 is minus 6, reduced the power by 1. When does that equal 0? I added 6 to both sides, divided both sides by -6. So that gave me my x value. Back to the original function to work out the y value. Used my calculator, got that. And I know that this is an unhappy quadratic, sorry. So that's going to be a maximum point. Okay. We've already done one cubic today, so go on, see if you can solve this one for me. Start by dy by dx, finding dy by dx. Ask when it's equal to 0. We're expecting to find 2 turning points because it's a cubic, so see how far you can get with this one. So I get 3x squared minus 12x minus 63. Could have gone with the calculator. I don't know, I was feeling quite sprightly, so I solved it old school. Noted I could divide everything by 3, and then I just spotted, I was about to use my calculator at that point, but then I just spotted it was one that factorised quite nicely. So I've got my 2 x values, and I'm just going to work out my y values. So let's put 7 as my x value. Remember, to work out the other part of the coordinate, you go back to the original function. So I'm going to type in x cubed minus 6x squared minus 63x plus 21, minus 371. So that's one coordinate. That's a really low value of y, and then I can go back up and change that to -3, then it re-evaluates it for me, 129. And maximum minimum, well, I know that this is a happy cubic, so it's going to be this sort of shape. So this one will be my because its x value is first, -3 comes before 7 on the x-axis. So this is my maximum, and this will be my minimum point. Well done if you got that. Okay, so let's look at some slightly different questions. Here we are given a, I'm not sure what they call quintics, when it's a graph where we've got the highest power of x is x to the power of 5, so I've no idea what this looks like without sketching it on my calculator, but we've got to show it has no stationary points. Okay, so they're using f of x notation, so I'll use that when I differentiate, so that's 5x to the power of 4 plus 3. I've got to show there's nowhere where that equals 0. Okay, let's take away 3 from both sides, divide both sides by 5. Why is that not possible? Well, x to the power of 4 is like x squared, isn't it? When you do a number to the power of 4, it's always positive. Even if x is negative, when you square it, it becomes positive. Multiply it by itself again to cube it, becomes negative again. Multiply it by itself again, it becomes positive. So this is not possible. X to the power of 4 can't be negative. So there are no turning points. Okay. Similar sort of question, another graph where we've got no turning points and we've got to find the value of a missing letter, k in this case. So okay, let's start by differentiating. So that's going to be 3x squared plus k, and there are turning points when that equals 0, but I've got to show that there are no solutions to that curve, that graph, that equation. This is a quadratic. It's a quadratic where a is 3, there is no b, there's no x term, and c is equal to k. What do I know about quadratics that have no solutions? Well, I know that their discriminant will be negative. So if I've got no solutions, I know that b squared minus 4ac must be less than 0. So go on, see if you can pick it up from there. It's quite an easy one because we've got no b in there. See if you can tell me something about the values of k. Pause and have a go. So b squared will be 0 squared, nothing. I always do my 4ac in brackets, so I've got 4 times 3 times k, so that's minus 12k. Now I want to know about k, so to get k on its own, I've got to divide both sides by minus 12. Now that obviously just leaves me with 0 there, but do you remember what happens to the inequality sign when you divide or multiply by a negative number? Got to flip it around. So in order for this function to have no turning points, k's got to be positive. It's got to be bigger than 0. Okay, so here's a submission question for today. It's a bit like the one we did at the start, but I've done some of the work for you. So you've got a cubic function, but they've given it to you in factorized form as well. Got a repeated root here. So that makes it a little bit easier, some of you may remember. But yeah, it goes through the process we went through at the start. We know the roots, so we can do most of the sketch, and now we can use differentiation to help us locate the turning points. And yeah, I look forward to seeing your solution to that. Now, you may have noted that I'm not using examples from our textbook. I don't like the order the textbook does things in, so I've used a different resource. If you want more practice, then I've attached to today's lesson the exercise I've taken my examples from. So we've done several of these questions already, but there are more questions on that sheet. Again, this is not compulsory. This is just if you want more practice. And you'll note I haven't set you a homework this week. But we're not quite at the point where I want to do that yet. So, you know, you may want to do some extra practice. And I've put the solutions there. It's a bit small, it's a bit confusing because it goes, there's 1 down there, and then you've got 2, 3, 4, 5 there, and then you've got 6, 7, 8 there. But it's all on that attachment, questions and answers if you wanted to. Okay, so next lesson we'll look at how we can work out whether we're dealing with maximums, minimums, or inflections if it's not a graph that we know the shape of. Take care.